So our next speaker is Dr. Long Shi from Ames National Lab. So Dr. Shi is a research scientist at Ames National Laboratory, and he's going to talk about liquid extraction of rare earth elements. So this is liquid extraction in chemistry language, right? So in metallurgy language, is solvent extraction, right?
All right, thank you, Lana, for the introduction. Also, thank Marek for your invitation. It's great to speak here. I'm a chemist by training. As Lana said, I'm a scientist, research scientist in a DOE national lab called the Ames National Laboratory. It's in Ames, Iowa. Today we'll talk about how we can accelerate the critical mineral and material separation with artificial intelligence and automation, especially a chemistry perspective, right? So I still want to start my slides with this figure. I guess people in this room has been seeing this many times, but every time I see this, I see increasing demands of new materials and larger volume of materials for even medium-term applications. That's only like 10 years from now, right? Looking at how this different kind of mineral we need, even like magnesium, right? I would never imagine magnesium will be a critical mineral. So what happens 20 years from now or 30 years from now, especially thinking about carbon neutrality by 2050? To really achieve the production of critical minerals at scale, we have been thinking about taking a very aggressive timeline, right? So we have to think about for every new technology, we need to spend 10 years and 10 years only to get them from fundamental research to modular plants. So that means we have to take 5 years for use-driven fundamental science, and then another 3 to 5 years for the bench to pilot scale development, another 2 to 3 years to build modular plants. So otherwise, we do not see any other ways to really make an impact by 2050 for the carbon neutrality applications, which is the key focus of the Department of Energy at the moment. Think about how we really manufacture chemicals and critical materials, especially for the fundamental science or lab scale demonstrations, right? You have to start with something, synthesize a molecule, right? If you want to do solvent extraction or hydrometallurgy. And then you have to test them, right? I have a new feedstock, emerging feedstock with low concentration, or some other type of a new composition of a feedstock that people have never worked with, right? And then you have to look at how they perform. And then once you get data, and then you have to use the human intelligence to think about how those information can be processed and compiled, and then we generate new hypotheses for better synthesis. So we have been thinking about to accelerate this life cycle, right? Then how can we use automation to achieve automated synthesis, especially use AI to guide the synthesis? And then we can use High-Throughput evaluation to achieve the quick evaluation of the system. We get more data points than anybody else, or more than what human can normally do. And to collect those data, and then we use AI to do prediction of new molecules, and then use those information to guide the automated synthesis again until we reach the optimal goal, right? And so I will go through all these 3 different parts of this life cycle. The first part is automated synthesis. As in Ames Lab, we have been working with many different kind of new software, new algorithm development. We can automate reactors, pretty much most of the ones used for chemical synthesis. And then we can use AI to guide the optimization. So this will be unmanned, fully automated, on-the-fly optimization reactions. This is a software called the Reaction Rover. And then we can use optimization algorithm, such as active machine learning algorithm, to do this kind of optimization, right? You either can collect data by batch mode, right? You can still let the students, staff, scientists, technicians to collect those data and then fit those into the algorithm, or you can, again, use on-the-fly, fully unmanned optimization, closed-loop optimization to achieve this kind of optimization goals. In the end, also sometimes realize different process has different kinds of data, but we can still do synthesis, right? We can also do separation using algorithms to guide the benchmarking of the optimization process. So our goal is to create a toolbox that's robust and easy to use by experimentalists who are not familiar with programming, like myself. So even as the leader of this project, I do not do coding. So But with the software, we let undergrad students, grad students, engineers, and technicians to use our software. Typically, even for intern students, right, we have a lot of SUDI students from as funded by Department of Energy. After only 1 day of training, they can start to use our software and start to generate molecules. Sometimes we let them start experiment on Friday afternoon, and the experiment continues till Monday morning. And they collect more than 100 data points, right? I don't believe most of the graduate students collect 100 data points in 6 months, no later than just a weekend. So this is the interface of the software we have. It has a different component. In the red box is the software, is the algorithm. It's called a snot fit. This one allows the automated decision making on the fly. The one in the blue box is the online online feedback loop. So here we use LC, liquid chromatography, to give a concentration of the starting material, the final product, intermediates, and side products. You can imagine using other type of online feedstock like X-ray fluorescence or some other type of technology to give you concentration of metals, or IR UVs to give you other type of information. At the bottom, in the purple zone, you can see different performance. You see the concentration. You see the temperature of the process. You see the pressure of the pumps. On the right, you can also do manual control. Sometimes, if I have to do experiment in the evening, I just remote control to the computer and access everything. I even have a camera pointing out to my to the hardware. I know exactly what's going on. So these are the equipment that we have built. We have built different kind of hardware for different kind of concentration, different type of applications, right? For lower temperature applications, higher temperature applications, and how to use those for different kind of ligand synthesis. Eventually, we think we can also do continuous flow separation studies. So here is the example of the reactions. So I will not torture you with the chemistry here. So I'm saying that this is an important reactions for doing ligand synthesis. So within 48 hours, we collect about 180 data points. And the optimal condition was achieved within 20 hours. So that means we can most likely optimize every single chemical reaction within 1 day, right? So this is a far more smarter than doing manual optimization, which take more training and other stuff, right? So on the right, we can also do further data mining, right? Understand what's really going on for this reaction optimization. Again here, so basically once we collect 200, 300 data points, we can use AI to analyze data. So we understand exactly how AI can probe these kind of reactions. I call this artificial intelligence directed evolution of chemical reactions, right? We imagine that in the future, so all these kind of jobs can be designated to AIs instead of torturing us to think about how to optimize reactions in the lab. So overall, I have mentioned that different kind of applications using automation, reaction optimizations, different kind of AI algorithm to do reaction optimizations or even separation studies. So reaction rover is almost like a one-stop shop for everything. So it can really be used by lab applications or even in research labs in industry. Going from there, it's very important that we have to make chemicals, right? Not just milligram level. We have to consider them making like 10 grams or above, right? For example, in this case, we have been making synthesis of this molecule called diglycolamides at 200 gram scale. So this is very important to do the further optimization studies, right? I will show you in a second. On the right, you see this spider chart. So this compare the life cycle assessment of the new synthesis that we have conducted compared to the state of art. So it shows that we're far more environmentally benign compared to the existing technology. The next part is high-throughput evaluation, right? So we use more automation, even robotic system to do this kind of studies. So this is the labs that we have. You can see two different kind of robotic system. In the smaller figure in the middle, there is a robotic arm controlling plates. You can move them into the centrifuge and allow automated phase separations. We can do this for chemical reactions, either organic, inorganic. We can do liquid extractions or hydrometallurgy. We can do selective dissolution, selective leaching, selective precipitation. So I figure that this probably can apply to most of the hydrometallurgy studies in the lab. With this, you can see that we have the arm that hanging on the top, and then you have the pumps that deliver the liquid. There's a needle head needle head at the back of the arm that can deliver liquid or transfer liquid from one port to another. You can do solid dispensing as well. You can deliver the ores from one or pure compounds or ligands or something, prepare solutions one way or another, right? So here is the example, how does this work? So I think this is moving. Okay, so now you can see that the needle head is picked up by the robotic arm. It moves, rotates, find out where you want to transfer the liquids from, and then they pick up the liquid, and then it will, once it's ready, it will lift up and then move to the next position. So this is about a 1 minute long video. Fortunately, I have no way to control from my side. So you can hear, well, in the lab, you can hear how this sounds. And then once it's ready, it will move the, I would think this is very futuristic. I used to stare at this for a long time because thinking about like how it works and how to replace my job in the future, right? And then after it delivered, it will move it back to the original position and then ready for the next job. And so this can go on and on 24 hours with nonstop, right? And then it will move back to its original position. All right. So with this, we can do all kind of hydrometallurgy, reaction condition optimization. We can do solvent composition, acid concentration, acid type, different type of extractant, and also do extraction studies or stripping studies. I would think it will be prohibitive to go through everything in a very time-sensitive fashion. So I think we can achieve about 200 extraction studies within 2-3 days and getting all the ICP results to know exactly what's going on. And with this, we developed a new workflow to do extractions of heavy rare earths and do stripping of light rare earths elements. And then this is work it just published recently. In the end, so this is the last piece, is the AI prediction part. So once we get all these results from the high-throughput evaluation, and then my team member, Marilu Perez, she will use all the data to do prediction. She can predict exactly what's the binding structure should be, and then in the future, we hope to design the alkyl chains and other type of secondary coordination environment to help further design the molecule. And then the molecule can be synthesized in the automated synthesis again. And then with this, so this is the workflow we have conducted. You can see all different parts we put together in the last 3 years. We even get industrial support to continue this work. It's really making impact in industry. I hope to bridge with more industries through this meeting and after this. So this is the team. So we have very talented scientists doing machine learning studies, automation studies. In the future, we'll do automated titration experiment as well that will better complete a whole picture of the hydrometallurgy needs in the lab. So this is really the idea. If someone comes with us and spend one month with us, you probably can get more data than you can do within 1 year just by a human being, right? So this is what we want to achieve. Also on the upper right corner, you see the students there. We have 3 undergrad students who work with us. So they are paid by the Department of Energy to welcome. So we really welcome more undergrad students who work with us. So even one of them found a job in a critical mineral company in Wisconsin. I was very proud of it. In the end, so I will conclude that so this is not a means to have less human beings in the lab. It's actually to really magnify the power of our brain in the lab. So we do think that we still need more and more talented people in the lab who will be behind the scene, right, making sure everything is working properly and get to the goals that we need for 2050. Thank you very much for your attention.